Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again, and thank you for joining us on the podcast known as Space Nuts. My name's Andrew Dunkley, and I don't know anything. And joining me is Fred Watson from the Australian Astronomical Observatory, who knows a little bit more. Hello, Fred.
Only a little bit, though, and only a smidgen more, but maybe enough to impress you, if not our listeners.
I'm easily impressed, Fred, I'm sorry to say. I must warn you that I've had a flu shot, and now I feel like I haven't had a flu shot, so don't get too close to your speakers or your earbuds or whatever. But we'll press on regardless. So you'll be doing most of the talking today, Fred. We're going to talk about the Hubble Space Telescope and the fact that it's detected a star halfway across the universe, which is a heck of a long way away. And still on Hubble, we'll look at its replacement or lack of. It looks like that's been delayed for another couple of years. Huge reserves of water ice on Mars that could lead to human colonisation, and that's a pretty divisive subject at the best of times, and a question about dark energy from our audience. So, lots to do today, Fred. Let's talk about this star, Icarus, that Hubble has been used to detect halfway across the universe. We know that because there's a half-mile post that shows us where it is. What's the story?
Actually, it's more like 2/3 of the way across the universe.
Wow.
It's you're underselling it, Andrew. So it's a star which we see because of this quirk of nature that you and I have spoken about before, which is called gravitational
lensing.
Lensing, exactly. So here's the story. Back in 2011. The Hubble Space Telescope took a very, very deep image. That means, they concentrated for a long time to gather all the photons of this particular area of the sky. And it's an area that has, in what you might call the foreground, even though it's several billion light years away, a cluster of galaxies. So this cluster of, each galaxy with 100 billion stars or something like that, but they're clustered together. There's probably 1,000 of these galaxies. So that is an enormous concentration of mass. And what that does is bends the space around it in accordance with Einstein's theory of gravity, what we call general relativity. And in bending the space around it, it acts like a giant telescope and effectively focuses on us, the light from objects behind, and faint galaxies and quasars and things of that sort behind the cluster. Instead of being sort of blocked off by it, they're actually magnified by it. You can see these curiously distorted images of very distant galaxies in between the images of the lensing galaxies themselves, the ones that are actually acting as the telescope. So that's the scenario. We've got a cluster of galaxies in the middle ground, you might call it, and then other stuff in the far distance, at a distance of about 9.3 billion light years. And that is the stuff that's being magnified. Now, in 2011, the image that was made of this area of the sky showed nothing but these very distant galaxies looking distorted and, slightly anemic. But then another image taken in 2016 revealed a star where one had not been seen before. And what that's telling us is that it's not an exploding star, Andrew, just to clarify, because supernovae, the exploding stars, you see them across actually greater distances than this because they are so incredibly bright. This is a normal star, albeit a big one. It's probably 100 times the diameter of the sun, and it's something like 1 million times brighter. Why did it pop into existence? It's just because everything in space is moving, and even at these enormous distances, the movement makes a difference to the actual alignment of the gravitational lens. So as this cluster of galaxies and the distant star behind it, as they very slowly change their relative positions, that changes the magnification factor of the gravitational lens. And suddenly the star comes into range of our telescopes. It's brightened up because of the geometry of the lens.
So 7 years ago, we didn't have a clue about it. 2 years ago, we suddenly can see it.
That's right, in 2016. So that's when these observations were made. We're just seeing the reports of it now. Extraordinary stuff, really. And as you say, it's because the stars and the galaxies have moved relative to one another. The astronomers who are doing this work, who are based at the University of Minnesota and other institutions in the United States, they have given this star the name of Icarus. He actually, a guy called Patrick Kelly, he's at Minnesota University, he liked the idea of calling it Warhol. And it's named after, of course, the American artist Andy Warhol, who said that everybody gets their 15 minutes of fame. And this star has its 15 minutes of fame when it is perfectly aligned, but apparently nobody liked that. I quite like it, so it ended up as Icarus. Do you want to know what its proper name is?
I'd love to. I can't wait.
It's MACSJ1149 plus 2223 Lens Star 1. Yeah.
I've forgotten it already.
Yeah, well, so have I. And just to explain, Andrew, that a lot of people think, oh God, these astronomers they just pull these numbers randomly out of the air.
No, they do have a meaning.
Yes, they do. It's a catalogue number, but the numbers mean something because most of those digits in there are actually the position of this object in the sky. It's the equivalent of latitude and longitude on Earth, something we call right ascension and declination, and that tells anybody who kind of recognises that exactly where this object is, what part of the sky it's in.
Now, you said it was quite a large star compared to ours. It's a blue supergiant.
It is, that's right.
So does that make it young, middle-aged, getting elderly, Zimmer frame, what? This
star will never reach Zimmer frame status because a blue supergiant...
die young.
Yeah, it'll live fast, die young. Exactly that. And, it's one of these stars that it is probably... it's probably maybe even one of a relic of the early universe, because we think that the stars in the very early universe were much bigger than the ones that we see around us now, just because there was so much hydrogen in that early universe, and it sort of was all more compressed together than it is now, and that's what the raw material of stars is. I suppose, so it's 9.3 billion light years away. That means that the universe was something like 4 billion years old when this star was shining. So it probably isn't one of the first generation of stars. We think they were much earlier. But nevertheless, it's still an example of the giant stars that were more common in the early universe than they are now.
Yeah, and a great discovery. And it prompts the question in my mind as to, is that the limit of Hubble's capability? Seeing 2/3 of the way across the universe is quite an incredible achievement.
To see a star at that distance is absolutely unprecedented. I mean, I can remember when I started my career. I remember when we first saw the first galaxy that was about halfway across the universe. Actually, it's slightly less than that, in fact. And that was almost a miraculous occurrence because the sensitivity of telescopes was getting to the stage where you could actually see these things. But of course, now with the Hubble, we can see individual stars. You remember a galaxy is billions, hundreds of billions of stars. This is one individual star that we're seeing. So it just shows the way progress has been made. Your question about whether this is at the limit of the Hubble's detectability is right on the money, because it is. It's right at the extreme end of the sensitivity range of Hubble. And that's why astronomers are keen on Hubble's successor, which for many years now has been called the James Webb Space Telescope. It's named after a former NASA administrator.
Let me guess, his name's James Webb.
You're right on the money. Absolutely. For some years before that, it was called the Next Generation Space Telescope, named after somebody called Next Generation. No. So yeah,
That's okay. There's a kid out there named Metallica, so I wouldn't have actually said you were wrong.
Mr. Next Generation. No. So James Webb, former NASA administrator. It will almost certainly wind up with a different name when it flies, and that's why it's in the news at the moment, and it's why I'm desperately trying to segue into this topic.
You're doing well.
You're doing well, yeah. It is in the news because it's been delayed again, as you mentioned earlier. We were expecting the James Webb Space Telescope to be launched towards the end of next year, around about next October. But NASA has now pushed that back to no sooner than May 2020. So we're still 2 years away from the James Webb Telescope. It's one of a number of delays. It's kind of understandable why this is happening, Andrew, when you think about what kind of a piece of kit this is. It's a telescope whose main mirror is 6.5 meters in diameter, compared with the Hubble, which is 2.4 meters in diameter. But this mirror is too big. If it was a single piece of glass or glassy material, it would be too big for the payload of anything to carry it up there. And so it's made in a segmented form. Segmented mirrors are actually typical now of some of the biggest astronomical telescopes in the world. You make lots of hexagons smaller than the main mirror. I think the hexagons on the James Webb Telescope are about 1.5 meters across. There are 19 of them. But the thing is, this has to reach its station in space, which is not in Earth orbit. It's actually 1.5 million kilometers on the dark side of the Earth. It's on the opposite side of the Earth from the sun. It will sit in the Earth's shadow so that it's not receiving radiation from the sun. It's at a point which is called L2, which is a code name for a stable point in the environment of the Earth, where you can put things and they don't move far away. There are 5 of these, what are called Lagrange points. This is one that is on the opposite side of the sun. There are a number of spacecraft there already, so it's not a world first. But what is difficult is that you're putting it 1.5 million kilometers away and expecting this mirror to unfold like a flower opening its petals, and then the components register to a fraction of the wavelength of light, to 1 nanometer, 1 billionth of a meter, something like that. So it is a big technological ask, and that is why I think NASA is playing safe with all the tests that they're doing to ensure that the James Webb Space Telescope doesn't get out to its station 1.5 million kilometers away and then just go bleh.
Yeah, which, if you remember rightly, Hubble got up there and couldn't focus. So
indeed, I do. Yeah,
it took a long time to get that sorted out.
But the thing about Hubble was it's in Earth orbit. It's in low Earth orbit. It's about 700 kilometers, if I remember rightly. It will, and that meant that spacecraft could reach it. The space shuttle could go and fix it. With the James Webb, you get one shot at this, and that's the end of it.
Yeah, I can understand why they're being super duper careful.
Yeah, that's right. So I think we'd rather have something 2 years later that works than something now that doesn't work.
Yeah, but by the sound of it, given the scale of this piece of kit, as you said, it's going to do some amazing things.
I think it will.
I can't wait. Should be amazing. You're listening to Space Nuts with Andrew Dunkley and Fred Watson.
0G, and I feel fine.
Space Nuts.
Now let's take a little break and find out more about our sponsor, ExpressVPN, rated #1 by TechRadar. This is the one I use. I've been using it for a couple of years and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity. Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, yeah, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
Next up, Fred, we're going to talk about water on Mars. Now, we know it's there. It's been found before. They've scraped the surface and found ice, and we're talking about water ice. And it's now been found in vast quantities, which is starting to make people think about, if there's that much water there, we could colonise this planet. And that brings up all sorts of controversies, I'm sure. But tell us about this frozen water.
Yeah, don't get me started on colonisation. As you know, I'm not a great fan of the idea of colonising Mars, although I do think we should be exploring Mars. And I think humans are the correct medium to do that. So we do have to go to Mars, but I don't think we should be going there in our millions or billions. I think we've got to fix up our own planet first.
Yeah, well, maybe we won't. Maybe that's why we're looking at Mars.
Well, maybe that's right. However, to cut to the chase, and this story is one that I'm sort of reading between the lines a bit on it, because the only report I've read is fairly sketchy. But it comes from scientists at the US Geological Survey. And once again, it's a discovery that sort of underlines the enormous amount of water we kind of already know is on Mars. I mean, one of the statistics that staggered me a few years ago is if you melt all the ice in the southern polar cap, just the southern polar cap of Mars, it's enough to cover the surface to an average depth of 11 meters.
That's just amazing.
Of water. So there is colossal amounts of water there. We know also from the Phoenix lander, which I think you and I talked about in a previous existence, landed in 2008 in Mars's northern Arctic region. That had a little backhoe scoop on it that sort of scratched the surface. And sure enough, within a few millimeters, actually, it wasn't even centimeters, there was actually water ice underneath, a kind of permafrost.
Or somebody spilled the sugar, we're not sure yet.
Well, actually, the most basic observation proved that it wasn't sugar. And let me tell you what that was. So this thing, as it scratched into the ice, it sort of made crumbs of ice, little fragments of ice came off. And it sort of looked at these, and then it looked at them again 3 days later, and they'd all gone. And that's because those crumbs of ice actually they sublimate. They turn directly from a solid to a gas.
Yeah.
Because of the low atmospheric pressure on Mars. Water, it doesn't turn into water first; it just evaporates straight from ice. So sugar doesn't do that.
No, true enough. All right, well, proving that theory wrong.
Very nice observation was that.
It was amazing. The photos just incredible.
They were incredible, that's right. So, and I think the new discovery is incredible as well, because this is a chasm. It's probably an ancient water channel on Mars. And, we know that Mars was once warm and wet, probably 3.8 to 4 billion years ago. So there's lots of the geological evidence of there having been water on Mars. And I'm pretty sure that that's what I'm looking at in the image that is accompanying this story. But what it's also saying is that this channel cuts into a kind of plateau, and we can now see that it has very high cliffs on the edge of it, but those cliffs are ice, they're not rock. So we've got 100-meter high cliffs, which are basically solid ice, overlain with probably a fairly thin layer of soil. And that is why this discovery is being described as a mountain of frozen water. It's, it's basically this ice plateau. What's nice about it from a scientific point of view is that almost certainly if we sent, a spacecraft there, particularly if it had humans on who could climb all over this and have a look at it, we'd find that this ice is stratified, that it's in layers, and maybe that we could see evidence of the way Mars's climate has changed in those ice layers, in a kind of similar way to the way we do ice cores in Antarctica to look at the way the Earth's climate's changed. That kind of thing could almost certainly be done here. But of course, as you say, what's exciting Mars explorers is the fact that here are abundant supplies of water ice, which not only gives you water to live by, it also
rocket fuel.
Yeah, it gives you rocket fuel, exactly, because you can dissociate it into hydrogen and oxygen, and then you've got your rocket fuel. You're ahead of me in the game, Andrew Dunkley.
Well, we've talked about it as something that they could envisage for future missions to the moon. But,
exactly.
If you've got this kind of water on a place like Mars, wow, and the possibilities are staggering, really.
Yeah, I think so. I think, the more we know about Mars, the more we see that a lot of its ancient oceans are still there. They're just frozen, not very far underneath the surface of the planet.
It opens up a whole can of worms, though, because if we are going there to look around and see if there was life and if there are fossil records and things like that, there's every possibility that they could be embedded in water ice like this, I suppose. But it also opens up the possibility that there are maybe remnants of viral life that we don't want to dig up. That's a concern on Earth. So why wouldn't it be a concern on Mars?
It would be a concern on Mars, and that's why we have these planetary protection rules, because not only are we keen to avoid taking earthly microbes to worlds like Enceladus and Titan and Mars, we're also keen not to bring anything back that could be harmful to us.
Which they recently portrayed in the science fiction film Mars, although it wasn't a virus, it was just some sort of weird plastic creature that killed everybody. But that is definitely an issue for the future.
Yeah, that's right. But actually, the step that comes before that almost is what this reveals about the possibilities of there being life on Mars. And actually, there's a very nice comment from Simon George, who's a professor of chemistry at Macquarie University. He said, only on Earth we find life associated with ice sheets. So it doesn't actually have to be liquid water in which life can exist. And it will be very interesting to look at where these ice scarps are melting. The melting could potentially expose new bits of ice and possibly be a very interesting place to look for new evidence of life, either in the recent geological past or even living on Mars today. And of course, just to tie up the loose end there, he refers to ice melting. And in fact, we think that there are places where liquid water briefly does appear on Mars, and it would be perhaps these scarp slopes. If they were in direct sunlight near the equator, then you might see exactly that. So
in fact, I think there was a photo some years ago of a liquid water burst. I think it was in a crater or something on Mars that immediately froze, and then of course it disappeared. I believe I saw that photo some time back. Yeah, so they know that's happening. Yeah.
That's right, and we've actually discussed there's a natural antifreeze chemical called perchlorate, and these different perchlorates, if they're actually dissolved in water, reduce its freezing point by something like 70 degrees. So you can have liquid water on Mars. Yeah, actually, so many observations that have been made of this sort of thing. There was evidence just going back to the Phoenix rover. Sorry, it wasn't a rover. It was just a stable lander that landed on Mars and explored the immediate vicinity. But there was photographic evidence from that that water droplets formed on the underneath of the rover's structure, actually on its legs. Sorry,
wow, that's amazing.
Rover, yeah,
I've never heard that before.
And there was some tantalising evidence that little droplets were running down the legs of the lander, not rover, because it didn't go anywhere.
Yep.
But it had these struts underneath it. I'll try and dig those out because they certainly caused headlines at the time.
Yes, indeed. Wow. It gives people who are planning future missions a lot to think about. And when it comes to choosing a landing point or a point where you'd want to base humans, the possibilities are starting to become endless, which is very exciting. Very exciting indeed. All right, more on this, no doubt. You're listening to the Space Nuts podcast with Fred Watson from the Australian Astronomical Observatory, and I'm Andrew Dunkley.
3, 2, 1.
Space Nuts.
Finally, Fred, we are going to tackle a listener question, and this one comes from Richard Visser. Hello, Richard. Thanks for getting in touch. He says he's a long-term podcast listener but a first-time contactor. Smiley emoji. Now, here's his question. I know we don't yet know what dark matter is, but please hold a discussion giving details on the leading alternative theories and what experiments are being planned to investigate this further. Kind regards and keep up the great work. He's talking about me, Fred. There are many out there that greatly appreciate it. Dark matter has become the topic. Dark energy, dark matter. It's the sexy topic in astronomy at the moment. I suppose that's because it's also such a big mystery. So are there a lot of theories and experiments going on to try and figure it out?
There is a lot of work going on, and it's a great thing to talk about. And, we could do this almost for days. But let's just review the story of dark matter. It was first postulated actually back in 1933 by Fritz Zwicky, that astronomer that all modern-day astronomers love because he was so gifted with words when it came to destroying his colleagues. He referred to his colleagues as spherical bastards. And when somebody said, why are they spherical bastards? It's because they're bastards whichever way you look at them. That's what he said.
That's very clever.
Yeah, he's a clever man. But he realized that he was observing a cluster of galaxies in the constellation of Coma Berenices and realized that these galaxies were moving too fast for the cluster to kind of hold on to itself. The speed that the galaxies were moving at suggested that the whole thing should just fly apart. And, we know the universe is pretty old. It would have had time to do that. But something else was holding them in. And then people they wrote that off as something nobody understood. It really didn't catch any attention at all. And it was in the 1970s when two astronomers, one here in Australia, Ken Freeman, and more famously Vera Rubin in the United States, realized that galaxies are rotating too fast to stick together if all you can see is there. And that was when the dark matter problem really came into its own. So since the late 1970s, we've taken it very seriously indeed. And in fact, modern observations show that dark matter, whatever it is, invisible matter would be a better word, it outweighs normal matter by 5 to 1 in the universe at large. So for every gram of hydrogen or whatever else there's 5 grams of this other stuff, and it's everywhere. It's in the room you're sitting in, it's in the room I'm sitting in, it's all over.
It's actually sitting out on a couch playing Candy Crush at the moment.
I'm not going there. That's one for you, not for me. Just a quick aside, it's quite different from dark energy. That's a different problem altogether and another big mystery. And actually, of the two mysteries, dark matter is probably the one that will be solved first. Dark energy we really have no idea about. It's an energy of space itself, and that's, just boggles the mind. Dark matter is something at least you can get your head around because we know it comes in blobs, and we know that galaxies tend to form in those blobs. That's the way the universe seems to work. So the question of what it is really hit the astronomical consciousness in the 1980s and 90s. And in the 1990s, a big experiment was done actually at Mount Stromlo here in Australia with one of the telescopes there. And, of course, in other observatories around the world. But the Mount Stromlo telescope was one of the leaders in this. the idea was, okay, dark matter, we've got something that we can't see. It doesn't cast a shadow. It doesn't blot out the light of things behind it. It doesn't really seem to interact in any way with the kind of matter we know about, except that it has gravity, so it pulls stuff together. So the two theories emerged, the machos and the WIMPs. And the machos were massive compact halo objects, which were thought to be possibly, and by massive I mean big stuff, things like orphan planets, dead stars, black holes in copious numbers. These things were all postulated as being what were lumped together as massive compact halo objects. Why the halo? Because that's where we know the dark matter is, in the halos, the spherical halos of galaxies. The competing theory, well, let me just get rid of machos because the evidence all pointed to their non-existence. The experiment that was done at Mount Stromlo was looking for exactly what we started this segment talking about, gravitational lensing. They were, if machos were present in a galaxy in large enough numbers to cause the effects that we see, in other words, outweighing normal matter by 5 to 1, then we would see gravitational microlensing, as it's called. The black holes, the little planets, the whole the whole lot of stuff would actually have an effect on the stars behind them. You'd get gravitational lensing effects, very copious ones, and they were simply not seen. So that pushed the macho theory very much into the background, where it still is. We don't really believe that it is large objects that constitute dark matter. So the WIMPs theory came forward there. And WIMPs are weakly interacting massive particles. It's a kind of generic name for subatomic particles that weakly interact. That means they don't interact significantly with normal matter, but they're massive, they have mass, and it's that mass that gives us the gravitational effects. And that's the current best theory. That has evolved slightly, however, because we now are looking for specific species of subatomic particles. Let me just pause there for a moment in the narrative, though. This is Dark Matter 101, because there is another thing that came into discussion actually during the 1980s, and that was the possibility that we had gravity wrong, that our understanding of gravity was incorrect, and that at very low accelerations, actually is the technical term, that our laws of gravity break down and don't hold good. And in fact, a theory was put forward by an Israeli astronomer called Mordechai Milgrom, which was called MOND. MOND stood for Modified Newtonian Dynamics. He said that, okay, you can get rid of the idea of dark matter if you suggest that at very low levels of acceleration, the Newtonian laws break down. The problem with that at the time, and the reason why it really never took off, was that if you accept that, then countless other things that we think we already understand go haywire. The whole picture of our universe becomes inconsistent. And actually, there's been another nail in the coffin of MOND within the last couple of weeks, because there is a new, it's not a new galaxy, it's a galaxy that's probably quite old, but new observations of it. And as you correctly quoted to me just a few minutes ago while we're off air, it is called NGC 1052 DF2, or DF2 for short. It is a galaxy that contains no dark matter. There is enough mass that we can see in the stars to hold it together. So no dark matter in it.
Which sort of flies in the face of what we are theorising in regard to dark matter. So
it's a misfit.
Yes.
It is a misfit. But what it proves, Andrew, is that MOND is not a possibility. And that's because it fits the Newtonian dynamics perfectly. So if all you've got there is all you can see, then this galaxy behaves in exactly that way. So it's a mystery why it has no dark matter, but it proves that dark matter is real because the dynamics work, the gravitation works.
So is this galaxy flying apart?
It's not. No, it's got enough matter in it that we can see to hold it together.
Right.
So it doesn't need dark matter to keep it intact, and that's how we believe there is no dark matter, because the evidence shows that there is lots of evidence, actually, partly the fact that there's no gravitational lensing, because we can see distant objects through this galaxy. It's fairly thin on the ground.
I get it. Yeah.
But also, when you measure the speeds of the stars in it, they're traveling at the right rate if the only thing that's there is all you can see. So it's a kind of slightly quirky, but certainly a proof that dark matter is something real. So the quest continues, and really it's continuing now at places like the Large Hadron Collider on the Swiss-French border, where they are looking for evidence of something called supersymmetry, because supersymmetry is a theory of the particle universe, which particle physicists are very attached to, because it explains some other anomalies in physics. But it also has particles within the theory that would actually fit the bill for dark matter. Actually, things called neutralinos and axions are two of the top candidates for that. But we've seen no evidence of supersymmetry yet at the Large Hadron Collider. It's a bit disappointing. It probably suggests that we need an even bigger collider to do all this. So the jury's still out on what this stuff is. There is one final thing that I should throw into this. I hope this is the discussion that our listener wanted, the full account of dark matter. One other thing is that we might find dark matter by itself annihilating, because we believe dark matter particles, if they do come together, they'll collide and leave a certain signature in the gamma ray spectrum. Well, so maybe, just maybe, that will be the way that we actually identify dark matter. My hope, and I'm pretty optimistic, is that within the next 5 years we'll know what it is, and discussions like this will not be necessary anymore.
And we'll fuel our cars and everything will be clean.
Well, hopefully, yeah, that'd be great. You could put dark matter into a petrol tank and get 5 times as far on a tank full.
You never know. You never know. Richard, thank you for the question. Hopefully we provided you some direction. We weren't able to answer it because dark energy is still just a huge mystery. Dark matter, as Fred said, may be the next thing we solve. So thanks for the question. We really appreciate it, and we certainly do appreciate any of the questions you send. We've still got a few to get through, which we'll look at in future episodes. So keep in touch with us via Facebook or however you like to contact us. Slingshot it across the Pacific, whatever you like. Fred, thank you as always. It's been great fun.
It's been good talking to you as well, and you've done very well with your non-flu there. Yeah, I can see you suffering.
Yeah, it's a good thing this is not a vodcast, because I look pretty bad at the moment. My eyes are watering and I can feel this horrible tickle in the back of my throat that is so wanting to burst out, but I'm holding it back.
Good man.
For now, though, I think we'd better stop before that just turns into an implosion, and we'll talk to you next week.
Sounds great. Thanks a lot, Andrew.
Fred Watson from the Australian Astronomical Observatory, and from me, Andrew Dunkley, thank you as always for listening to Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.